Hello, today's video is going to be about cascade loop control. I have a bunch of text here, but I can explain what it says looking at the formulas. Basically what I want to cover is whether or not cascaded loop control is necessary. And basically what happens is that cascaded loop control shouldn't be used unless you have a feedback for every loop. I have seen most controllers where the position is differentiated to become a velocity, and they implement a velocity loop using the position feedback. But really what you should have is a better velocity feedback to use on inner loop like that. If you have only one feedback device, you really are better off combining the inner and outer PI loops into one PID loop, and I'll show why in a moment. But first, let's just start about at the basics. What I have for an example is a simple motor with a gain and a, well, this is a bandwidth, but if I divided this through, you would say that by alpha, you would say that this is a time constant. And the time constant would be a factor of the inertia and the amount of torque that can be applied. So this is a simplified model in the S domain. So we have the plant, and this is for velocity. And then we have the controller. We've got a simple PI controller. And you have to have a PI controller on the inner loop, because if you don't, the velocity will never achieve the target or the requested velocity. So the next step is to combine the two transfer functions for the controller and the motor into one closed loop transfer function, and we use this general formula here for the closed loop transfer function. And by doing the substitutions here, I can see what the closed loop transfer function is. Now notice that in the denominator, I have the full PID, and in the numerator, I only have the integrator. And when I do this, it means that the integrator and the proportional term are using the feedback, but in the forward direction, only the, well, this is using the error up here. So the errors get used on these terms here that are both here and here. And then the this is using changes in the actual position for the proportional gain. And what that does is it reduces the bandwidth. And the reason why you want to do that is because the outer loop is generating target positions or reference positions that the inner loop must follow. I mean, velocities that the inner loop must follow. And these can be noisy depending upon how good the feedback is. So it's best to remove the proportional terms or any term other than the integrator term from the forward path. So this is the closed loop transfer function for the inner loop. And now what we want to do is combine the two loops. So this is the inner loop velocity loop. This integrates the velocity into position. And then again, I have only the integrator for the outer loop in the forward path. And then I have all of this as the plant for the outer loop, and that's down here. And now we have the outer loop integrator and proportional terms here. So this is the closed loop transfer function. Now we can also see the simplified closed loop transfer function, and this is the characteristic equation here. And what I want you to notice is that there's a overlap of terms. You can see that the integrator for the inner loop and outer loop affect this term here, and then you got the inner loop integrator and the proportional for the outer loop, and that makes sense. The outer loop proportional term is the same as the integrating velocity on the inner loop, because if you integrate velocity on the inner loop, you get a proportional or a position. So these two terms are together. Then we have the inner loop here, and we have inner loop gain here. Now, when you're tuning, you can see that there's going to be some interaction. So if you're tuning this manually, what you want to do is tune the inner loop first and then tune the outer loop. You know, you've got to keep that inner loop fixed so that you don't see, you're not, if you change one thing, you're going to have to change the other, in other words. So there is some redundancy due to the two gains. So what you need to know is the cascaded control even necessary? And again, if you have only one feedback, you're better off combining these into a PID, and I can show you that here. Let's see, window, oops, window, make this big. You see, this is the same plant, but after I go through the procedure, I have a third order characteristic equation, and the calculations are quite simple for the PID gains. And now if I go back to Cascade loop, you can see that I got a fourth order, and that's due to the fact that the inner loop and the outer loop both have integrators. So each loop will add an integrator, which adds an extra pole. Now let's find the inner and outer loop gains symbolically. In this video, what I'm going to do is I'm going to compute the inner and outer loop gains at the same time. And since I got a fourth order equation and I got four unknowns, I got the inner loop Ki and Kp and the outer loop Ki and Kp. I've got four equations and four unknowns. So what I do is I take, this is my desired characteristic equation here. So I'm going to place four poles at minus lambda. And when I expand that out, I get these coefficients. And all I do is I match this coefficient with this one, which is done here. Then the first power of s with the first power of s here. And then do the same thing for the second power of s and the third power of s. And then I solve the four simultaneous equations for four unknowns, and I get these four equations. And what I want you to notice is that the outer loops are dependent upon lambda only. And that's something that is going to be significant in the other videos that I show, because if you're trying to tune this correctly, if you actually have the gain, or you know the gain and the bandwidth or time constant for the open loop plant, then you should be able to calculate the gains directly, like what I'm doing now. And outer loop gains are really just dependent upon the bandwidth. Shouldn't have to hunt around for them. So let's test this out. What I'm going to do is assume that I have a gain, open loop gain of, let's see, that's 10 millimeters per second per percent output. So at 100% output, I go 1 meter per second, or 1,000 millimeters per second. I have my bandwidth, which is quite low, but I do that to make the responses more visible. I want to place all four poles at the minus alpha point. It says -2, I can do that also. I'm going to use these symbolic equations that will use the parameters up above, and you can see I have the inner loop integrator, inner loop proportional, outer loop integrator, and the outer loop proportional terms. I'm going to do this simulation. I'm not going to talk about this too much because I do this in just about every video that I make. So let's see how this is implemented. Now I'm not using feed forwards yet. That's going to come in another video sometime. And what I got here is this uses the control output from the loop before to calculate a new state. So it's calculating a new position and velocity. See, we have, it's a 2x2, so we calculate positions and velocities. So we're calculating a new position and velocity, and then what we're doing here is we're calculating the outer loop first. The outer loop generates a velocity, a target velocity, for the inner loop to follow. So this is just a simple PI control. You can see that the integrator is acting on the error between the target and actual position. And then this is just looking at the difference in the position from the current position to the last position for the proportional term. So it's only the proportional term is only acting on changes in the position. Now, what we want to do is we want to limit this to reasonable velocities. And since we know that the maximum output is going to be 100%, and we know that the gain, the open loop gain, is 10 millimeters per second per percent, this upper and lower limit is very simple. It's just K times 100%. Now what we do is we have the inner loop, and the inner loop uses the target velocity, which is just generated here. So this is looking at the error between the target and actual velocity. And then this is looking at the, and we've got to remember this is velocity loop. And then we have the error, or not the error, but the change in the velocity between the current velocity and the last velocity. And this needs to be limited to plus or minus 100% output, because this is actually outputting the plus or minus 100% to the drive. And then what we do is we return the state. This is the position and velocity. This is the control output, 0 plus or minus 100%. And this is the velocity, which is the inner loop, or the reference velocity from the outer loop to the inner loop. And that is plus or minus 1,000 millimeters per millisecond. So now what I want to do is simulate 2 seconds worth of motion. And I'm just kind of jumping around. And I like to always do steps to begin with. And the reason why is I can see if the response is going to overshoot. I can see if the integrator is going to wind up. There's a lot of things that I can see just by making the system do steps. So this is the outer loop response. You can see this is the target position. You can see that it's stepping the target position. And the actual position is going right up. It's getting into position, and then I'm changing it. It's getting into position. It's coming down, getting in position. You can see it's getting into position without overshooting. And that's because we basically set all 4 poles to act like a single pole low-pass filter times 4. So there shouldn't be any overshoot, especially if there's no zeros. And I've discussed zeros causing overshoot in other videos. The magenta line is the inner loop target velocity, or the output from the outer loop. So you can see this is what the inner loop should be following. And if we go down here, I've changed the color for the inner loop. No, I guess I didn't. Okay, so I got the inner loop target velocity, which is the magenta line. But you can see the actual velocity for the inner loop is following the inner loop target velocity pretty well. And you can see that it's limiting to, well, the control output limits to plus or minus 100%. And again, I'm doing this on purpose just to check how the integrator wind up and overshoots. And you can see the control outputs saturate, trying to get the inner loop to go to the inner target velocity. So, but you can see that the response is really pretty good. Now, if I want to make the response faster, I can just change that lambda up above from being minus alpha to, or to being alpha to 2 times alpha, even 4 times alpha, and the response would be even faster. But since I'm driving it to saturation, it doesn't make much difference right now. So next I'm going to do a sine wave. Basically this is the same thing. You can see the outer loop. There's the outer loop target position, which is the magenta line. The actual position is the red line. You can see there's a little bit of phase delay there, and that's expected. I could make it so that it tunes up perfectly if I used feed forwards, but that's not the purpose of this presentation. Then you can see the, well, this should be the inner loop target velocity. So this is the target velocity that you're trying to follow. And then here, this is the inner loop, and you can see that the inner loop is following the target velocity accurately, and this is the plus or minus 100%. Well, it's actually not going up to plus or minus 100% to follow this sine wave. And this little bobble at the very beginning is due to the fact that I start the position and velocity both at 0, whereas a sine, the derivative of the sine is the cosine, and that's going to be 1 at 0. In other words, it's non-zero at 0. So let's look at the bandwidths. There's an awful lot of myths that I see on the internet about how much faster the inner loop has to be than the outer loop, and most of it's just, it does have to be faster. Mathematically, it's going to turn out to be faster, but just to arbitrarily say it's going to be 10 to 1 or 15 to 1 is not quite right, and I'm going to show you why and prove to you that it doesn't necessarily need to be that way. Okay, so this is the inner loop, closed loop transfer function, but what I've done is I've substituted j omega for the s parameter, and I'm finding the root where the response drops down by a factor, well, to 0.707, or 1 over the square root of 2. And you can see the inner loop bandwidth in radians is 130 radians per second, about 20.8 hertz. And the outer loop bandwidth, and again I borrowed this transfer function from above, but I substituted j omega for s, and I make a guess at the, this is a guess for the initial velocity, or bandwidth, and I do the same procedure here, and I get a bandwidth at 27 radians, 27.3 radians per second, and you can see the bandwidth is 4.3, about 4.35 hertz. And the ratio of the inner loop to the outer loop bandwidth is 4.78, and that's far lower than 10. And it changes. I can, if I made added a the gain for the forward loop, put the proportional in the forward loop, that would change the results down here. So let's plot the Bode plots, and this is just the mathematics to do it. We can see that the inner loop is well behaved. It doesn't overshoot. In fact, if I click here, I can see that the magnitude drops by this in, this is dBs here, and the gain over here, or this is the phase in degrees. So this is very well behaved. Outer loop Bode plot, you can see I have, this is the inner loop closed loop transfer function, and then I have to integrate this to become a position, and then I add the outer loop integrator here, and then I have to add the integrator proportional term here. And again, this is very well behaved, and this is very predictable. Remember, I set the alpha, the bandwidth, to be 10 hertz. I did 2 times pi times 10. So that's minus 62.8 or something like that. And if you have 4 poles at that location, you would expect it to be 3 dB per pole, or this would be about 12 dB. So let's just take a look at that. And right there, oops, it's about 12 dB down. And if we go to down here, this is 90 degrees. There's about 45 degrees phase shift per pole. So this is exactly what we would expect. We'd have 45 degrees of phase shift per pole at the bandwidth. So let's just take a look at where the inner loop poles are. You can see that I'm solving for the characteristic equation for the inner loop poles. I didn't do that up above. And I solve, and I can see that they're at minus 126, but there's an imaginary term at 88.5. And fortunately, the imaginary term is not large compared to the real term, So we're not going to see much, if any, tendency to oscillate or overshoot on the inner loop pole. Just for comparisons, the outer loop pole is at minus 62.8. So the rest of this is for the next video. That concludes this one. Bye.